All right, hello everyone. Welcome back to another 3D Printing Revolution series workshop. My name's Solomon Denning, and I'm going to be doing a workshop about 3D printing gears and explaining the basics of why it's possible to do this, and maybe even you might consider doing it in the future. So first, I'm sure everyone knows this isn't even a trick question, but what is a gear? It's basically just any form of disc or wheel that has teeth. But the main point of a gear is it helps to transmit or receive force or motion from another item or another gear. So gears are basically just used to transfer motion. And most people, when they think of gears, they assume metal gears, but I'm assuming all of you have seen plastic gears like this one right here. Most little toys and trinkets or just small hobby items usually have plastic gears in them, which is why we're going to be using 3D printers to print, because they use plastic. And yeah, so why would you need to print 3D gears? The obvious answer is it's cheap. Plastic is way cheaper than metal. And even if you think about it, if you're casting metal, that takes even more, or that adds up even more in the price to cast metal as well as pay for the metal itself. If you're using plastic, you can find a pretty cheap 3D printer nowadays. They're everywhere, and you can print anything that you find online or anything that you make. And another thing about it being cheap is most small items or toys, they don't even use metal gears, like I mentioned. So if you have something in your house that breaks and you have the knowledge and know-how to create a gear, it's pretty simple to 3D print that out and replace whatever part you need to replace. And another reason why you would want to 3D print gears is it's common. You can find modeling software pretty much anywhere. All these CAD softwares and all that, you can find the correct dimensions for gears, create custom gears. And even if that's not your forte, you can go on Thingiverse or any other platform that uploads models and find people like this one on the right that have created a bunch of different gears, and then you can just find which one works for you for your project and print it out. So ultimately, the main reason for 3D printing these is the cost and the ease of use. You don't got to worry about much of anything. And so um, for some of the applications, I'm going to explain the difference between high speed, low torque, high torque, because that will help a little later on in this workshop. So if you're not familiar with gears, there's the idea of a motor that delivers high speed and low torque, but in most cases we want the opposite. We want low speed, high torque for small items or small little home applications. So if we look at this top right image here, we can see an example of a bicycle. I'm using bicycles because everyone's familiar with a bike mostly, and it helps explain the point of how gears work pretty simply. So you can see on the right here for high gear, we have a small cog on the wheel. And what this is going to do is it's going to give high speed and low torque. Basically, there's going to be no friction or barely any friction. So if you're trying to drive up a hill with your bike, it's not going to happen in a high gear because your wheel, you can think of it intuitively. This cog is bigger than the cog that's inside of the wheel. So anytime you push the pedal, this wheel is going to spin super quick compared to this wheel on the left. This wheel has a bigger cog, so this wheel is going to spin less for the amount of effort you put on the pedal. Because the wheel's spinning so fast, it can't create any torque or any friction against the ground. So in high gear, you don't want to be going uphill in high gear. You want to be in a low gear. And the same applies for like I was saying, most small items and appliances that use gears, or that would be using plastic gears, you want to use a motor attached to your gear and create a speed reducer. So we're going to be focusing on gears that would be called low gear, or things that reduce the speed. So you have a series of gears that are put together where the first one's spinning fast, and then at the very end, the last gear is spinning slower than the first one rather than faster than the first gear that is attached to the motor. Um, that's a lot of information. I don't know if anyone has any questions at that point. I can answer them real quick. If there's no questions, then I'll move on to the next part.
It makes sense. Thank you, Solomon.
Got it. So moving on from having like an intuitive understanding of how gears work, if we focus on the 3D printing of the gears, there's a few challenges. These aren't all the challenges, but these are two of the basic ones that you need to focus on. The first one is fitting. You can see here that if you're 3D printing something, this center hole might not come out exactly how it was planned on your model. You might have got the perfect fit for the gear you want, but your 3D printer might print this hole just a fraction smaller, which means that you wouldn't be able to fit anything or fit what you intended into the hole so that you could spin the motor. This is pretty simple to fix. You just need to file or sand your gears to get them to fit correctly. But you need to be aware that most gears, especially if it's a tiny, tiny gear, it's not going to print exactly how you modeled it. So you'll need to do some fine tuning adjustment to get it to work correctly. Another challenge that comes up is the infill. If you're going to be using your gears for a lot of, or it's going to be putting a lot of pressure on your gears for whatever you're using them for, if you use a low infill, like here on the right, bottom right, it's possible that your teeth might snap in the process of whatever you're doing. So you would want to use maybe 100% infill on your gear. The problem with small gears is that they might not fill completely. So this gear that's in the middle, I believe, was a gear that was 100% infill, but it didn't necessarily fill up all the way compared to the left one. So you also need to be aware, if you're printing gears on a printer, that the infill matters and that you should figure out what infill you need before you start printing them out. And then moving on to the next topic that you'll need to know is gear ratios. This is the important one, and it will like this basically explains how my example that I'll be showing after this works. So if you're unaware of gear ratios, it's basically just the idea of how fast one gear rotates fully compared to another one. So if you look at this middle image here, we have a tiny gear with 25 teeth, and we're calling this the driver gear. So this would be the gear that is attached to a motor, like a DC motor, or maybe just a hand crank if you're doing it manually. And then here on the right, we have another gear called the driven gear. And this gear has way more teeth. It's also much bigger. But this is the gear that's going to be moving based off the driver gear. So if we look at this image down here on the right, you can see that if we take the driven gear, the one that doesn't have a motor attached to it, and divide that by the number of teeth on the driving gear, we'll get the gear ratio. This basically means that every time the driver gear rotates 3 times, this bigger driven gear is going to rotate 1 complete time. And this is useful in pretty much everything. You want to understand how many teeth you need on your gears so that you can get a certain ratio. It would all depend on your application or your use. And for most things, there's more than 2 gears. This is just a basic example. They usually will call gears that are in the middle idler gears, but I won't go into that because it's not necessary for today's workshop. And so continuing this idea, what we need to focus about for 3D printers is how many teeth do you want on your gears? Say you want a 2-to-1 gear ratio, that would mean that your driving gear, the one with the motor attached to it, is going to rotate twice every time the driven gear is rotated once. You can do this plenty of different ways. You could use 30 teeth and 60 teeth, 5 teeth and 10 teeth. And I'm assuming that you're understanding the point here, but how many teeth are needed needs to be determined beforehand before you start printing because you need to model it with that many teeth. And most 3D printers probably aren't going to handle having a gear that's the size of your palm with 200 teeth on it because that would just be too tiny of teeth for your 3D printer to be able to print them accurately. You're going to have a bunch of errors and issues. So you want to pick your gear ratio, and then you want to find how many teeth you need so that you can complete the project and that it will rotate smoothly, but you don't need it to be as smooth as it can be. You don't need 200 teeth because it might not print. You might be able to get away with, say, 50 and 100 teeth. So, yeah. So, if there's no questions about gear ratios, I'll move on to the next part, which I believe is just the example print that I've done.
I actually did want to ask you on something a couple of slides ago on the infill, I think it was.
Yeah.
So again, since I'm not too familiar with this, I can understand why you'd want like an infill that has less than 100%, like for saving of materials. But what's the practical use of like anything, not just a gear that has less than 100% infill? Like,
I would
what's the
say
advantage of it essentially?
the main advantage would be time. I believe last week we were doing a workshop on drones. Jesus here in the Zoom call was hosting that one, and he was showing that whenever he printed a drone body, I believe that wasn't 100% infill, it would crack. So in those cases, like you wouldn't want to be using less than 100%. But as for me, like the example I'm about to show, I printed it with 20% infill, and it works fine just because it's a gear set that doesn't have a lot of force being pushed on it. So in most like cases, if you're building like a toy or something, or like a DIY thing or a simple solution, you don't need 100% because it's mostly going to waste your material and your time, because the difference of printing 20% infill versus 100% infill is, I think, a couple hours. So it's going to take you a long time. So it's basically the idea that you want to pick the lowest infill that you are comfortable with for that project so you can save your time. And if that answers your question, I'll move on to the example.
Yeah, that was great. Thank you.
So I took a few pictures of this print I was doing. You can see how this is like, I believe it was like 30 minutes into the print, but you can see that the first couple layers are being printed, and you can see that the shape is really good. It didn't have any issues. I was doing a print before this one, and I was having issues where it would start drawing the teeth, and then it would pull off of the board and then just start dragging all of the teeth with it. So you have to make sure that you calibrate your 3D printer to where you can print gears like this. It's usually not too difficult, but it takes some working around to get it working on everyone's printer. And then this was halfway through. You can see that this is the result of 20% infill. If this was 100% infill, you wouldn't see all these triangle or like hex patterns. It would just fill it in completely. But what this is doing is, if we look at the original one, it's printing it solid for a few layers, and then in the very middle it prints with gaps and spaces, and then at the very end it fills it all in again. So you can see that the gears that I've printed are semi-hollow inside, but because this isn't going to be used for like, or a ton of pressure is not being applied to this, they're not going to break or anything. So I was comfortable doing it with 20% infill. But then if we put this together, you can see this is how it looked. And then I can show off it working in action right now. Let me move my mic real quick. So you can see this is what it looks like. And it has a hand crank on it. And the idea of this is, I forgot to mention the reason why this is called the parametric isn't too much of an issue, or you don't really need to understand why it's called parametric, but 27 to 1 gear set, what that's meaning is if you see where this hand crank is, there's a tiny gear connected to it. And every time that gear spins 27 times, 27 full rotations, the gear on the very left is going to rotate 1 time. And so depending on your application, you may need a higher or a lower gear ratio. In this case, it's a toy, so it doesn't matter what ratio it has. It just is going to work either way. But it's a little hard to show on camera, but you can see it kind of working in action. You can see that this one is spinning way faster than that one. If I can keep it kind of still. I don't know how well that shows up on camera, but this one's spinning faster. This one's a little slower, and then this one is the slowest. And so that is an example of a gear, or what do you call that? A speed reducer gear set. It's reducing the speed of the gear, and reducing the speed of your gear, like I was mentioning in the bicycle, allows for more torque, and more torque allows you to apply more like pressure to move things. It's that's the basic idea of it all. So with
Something I
that,
wanted to add, Solomon, if I may. I heard that they 3D print gears not just for toys or just for practical purposes, but also to show off car engines. Like they would 3D print an entire like jet propulsion engine or a car engine to show students how the actual gears move inside a car, so that they'll have a better understanding when they're trying to fix the actual engine.
that's actually a good topic. I didn't think to mention that. So let me take a side note real quick and open up Thingiverse because I can show that off real quick. If you look up something like manual transmission, you'll be able to see that a ton of people make designs for, I don't know if I can find one right away. I would say maybe this one is.
You can top
We can
left.
do that one. That one looks good. But you can see that there's people create 3D printed like actual motors or transmissions. And then these you can actually see how they work inside, like Armand was mentioning. And so, yeah, this is like a good idea of something to build if you're learning about mechanical parts for like planes or cars, to be able to just print something out like this, take it apart, put it together, and have an idea of how it's made. It's really useful. That one looked like it was a Toyota transmission. There's a bunch of different ones. I looked up manual transmission because those usually have more gears that are visible for people to mess around with and look at.
Can you look up the jet one? Jet propulsion engine.
Yeah.
I was looking at one earlier.
It's
Just
not
say-
showing up for me.
Okay, jet engine or just jet?
I'll try jet engine.
Oh yeah, on the bottom left, or on top left. I was looking at that.
Here we go. Yeah, so this is another example. Instead of a car engine. This here is a jet engine, 3D printed. So yeah, this is like actually a great like learning tool that you could use for teaching people and like technical skills and all that.
They had some fairs, 3D printed fairs, some time ago before COVID, where they were showing off car engines that were 3D printed.
And then like as I was mentioning before as well, like if you look at this, it's really complicated. So if you're printing something like this, the person that designed it probably did a good job of making sure that it prints in correct dimensions, but you never know. So when people go to print stuff like this, they have to do some testing and configuring to make sure that all the gears are sized correctly and they fit together correctly. So yeah, let me close that out and open this up again. So with that, that was the end of my workshop. I can continue answering questions, but these are some of the sources I used. This here was the build that I built. If you, I believe if you just look up like thing 9454, you can find it too. But yeah, so is there any other questions?
What did you have to print that like high definition or like a small layer height, or because it seems to work pretty smooth?
Yeah, it was, let me think. I don't remember the exact layer height, but it was the one that is like defaulted on Kira. I think it's like 2 millimeters or something.
Oh yeah, okay.
But yeah, it printed fine just on the normal parameters. It was like normal layer height, normal 20% infill. But the reason this morning it actually wasn't working this smooth, you can see like I can do this and it just kind of works. This morning it wasn't doing that. I've been doing a bunch of fine tuning since last night. I had to file the, what is it, all of these fitting points here where there's holes. The gears snap into these holes, but the holes were too tight. Like I was mentioning, it has a shrinkage in the center hole, so you have to go in with a knife or a file and start shaving it out so that everything fits smoothly. It wouldn't even snap into place when I pulled it off of the printer bed. But now it's working great after I've done some adjustments. Any other questions?
Great workshop, Solomon.
And
Thank you.
yeah, thanks. And well, I guess with that, that concludes tonight's workshop. Thanks for coming, everyone that's here. And these videos are uploaded on our Q Project YouTube channel. So if you would like to check that out afterwards, more videos, this should, if you're viewing this on YouTube, thank you for watching our channel. And with that, thank you and goodbye.